everybody. Thanks for coming in for this part of the Intro to WinDbg series. I'm curious. Hopefully everybody's in Discord already because inside Discord, inside the Sans Workshop channel specifically, I have some very, very important files for y'all to download if you want to follow along with me pretty much to the T. This is completely optional. You don't have to do so. And in fact, before I get started with anything official for part 3 here, I'll just give you a little bit. I'll just keep on talking about some things. Give you a little bit of time to jump into that Discord server and download some of those files. And I will be making a couple of assumptions for this part here. I assume that everybody jumping into this has been around for parts 1 and 2. With part 2 being time travel debugging with Kevin. Hopefully y'all enjoyed that one. It's always good to have Kevin helping out and do some workshops. Super smart guy. And then part 1 was the complete introduction to the software itself, basically just how to navigate the GUI window and stuff like that. And so now for part 3, we get to dive into things a little bit deeper and inspect some calling conventions for 32-bit calling conventions and, of course, 64-bit calling convention around functions, their parameters, how arguments are passed through those parameters, and how we can make sense of some of those different things inside of the debugger, and how we can leverage some information from MSDN documentation to give us some insight into the various calling conventions and basically tell us what to look for when we're inside of the debugger. All right, so again, I hope everybody is inside the Discord server. I have 2 files out there for you. The callmemaybe.zip, which is the source code that you see up here on my screen right now. That's the source code for everything, and for the 2 binaries that we'll be working with throughout today. And if you haven't downloaded them, if you feel like hand jamming and hand coding all of that right now, feel free to do so. I do have some very specific compiler and basically project settings that I've tweaked just a little bit to make these unique for our situation here. All right, so let me make sure nobody has any questions so far. And if you're in the Discord server, please give a little thumbs up on that message that I dropped over there for the files that you need to have. And then the other file that I have out there, the .zip, is the trace files. Okay, the trace files are previously recorded execution of the binaries that we're going to take a look at today. Leveraging TTD is something that you all hopefully have done part 2 with Kevin. So we'll use TTD yet again for this part of the series. Awesome, cool. Thanks for a thumbs up over there. Good stuff. Got at least one person there that's grabbed all the files. Cool. All right, so I'll talk just a little bit more so I can see some more thumbs up over there, and then we'll go ahead and officially kick things off here. All right, so if you don't know me by now, my name is Jonathan Reiter. I'm an author of Security 670, which is all about using C++ to create implants for the Windows operating system. And it's been out there in the public for a while now, and it's a blast teaching it. Kevin is also another instructor for it. So what I'm hoping to do with these series, as well as the Intro to C series that I did, is to basically help people get ready for a class like that, like 670. Because if you don't have some of this experience, some of this exposure, foundational skill sets coming into the course, you might feel a little bit swamped. So this is basically a prep for that prerequisite. And then after this Intro to WinDbg series is over, I think we're going to do a total of 6 parts for this series, if anybody's curious. I'm going to start an Intro to C++, and that's probably going to be around 10 to 12 parts as well, with the ambitions of having 1 part every month, or 1 part every other month, depending on schedule and when we can get some of these workshops scheduled through Sans. But the beauty of all of these, they're always recorded, and they will always be free. And so that's just an awesome thing right there in and of itself. All right, cool. Let's go ahead and kick things off, all right? All right, so using WinDbg today to debug a couple of applications and diving specifically into how some of these arguments are being passed to a function like CreateFile. Okay, so I have my little project up here called CreateFile. Everything is in pure C. All right, that way if you've done the whole Intro to C series, a lot of this should be familiar to you. If not, maybe you've done enough C on your own that you're already familiar with some of this stuff, and you'll be right at home. Okay, so CreateFile. CreateFile is a Windows API to do just that, create a file. And we can see from a header file how this thing is prototyped or how it's defined by Microsoft. So I can click on that, and I can hit F12, and I'll open up the header file where it's been declared. It happens to be file API.h. How about that? And we can see that what it gives back to us as a return value is a handle. Okay, the handle hopefully is going to be our way to interact with that newly created file on disk. That way we can do other actions to it, like maybe write some data to it, read from it, or anything like that, even possibly deleting a file on disk. Okay, so we'll have to check for that. We'll have to check to make sure that the handle is actually a legit handle and it didn't error out for some reason. But we can see we have a number of parameters here. We got the 1, 2, 3, 4, 5, 6, 7, I believe. Yeah. And so we see various things of what we're going to have to pass to this to make CreateFile happy. All right. So now let's go back to the actual source code here. And I'll go ahead and explain some of these parameters and what I'm passing into it here. The first parameter there is the file name. Okay, this is the actual name of the file that I want to drop to disk. All right, file.log, name it whatever you want. I don't care. This is just for demo purposes. Okay, so the next piece, if you hover over the file name or the API name, it'll kind of show you the different parameters that it expects. All right, so the next one is the desired access. Well, we want to be able to possibly write to this file, maybe at some point in the future. So we'll say generic write. And we can see that this is a pound define. And where I got that is if I just hit F12 for this, it brings up the WinNT header file. And we see the pound define here with this constant value. And so when we jump over into the debugger, we're not going to see generic write. We're going to see this value here in hex. All right, then the next parameter there, we're just saying 0 for the shared mode. And then security attributes, not passing in anything there either. Security attributes are a way that we could possibly further lock down or restrict access to this particular object when it gets created. Yeah, and then create new. Create new is going to be the creation disposition argument. You can see here that the comment that I have is just another pound define. Create new with just a value of 1. Okay, so 1 is going to be the value that we'll see in the debugger. The reason why, at least I think the reason why Microsoft does this is instead of having just a bunch of what I call magic values throughout, they create some constants or whatever around some of those values, or like an alias, if you will. That way it's a little bit more apparent what you're doing when you're calling a function like this. And it could be a lot more readable for people looking at the code, doing a source code review or whatever. All right, and then we have the file attribute normal, okay, being passed in as a flag for flags and attributes parameter. Just saying, hey, this is a traditional file that's going to be on disk. We're not going to make it like an archive file. It's not a system file or anything like that. And I'll hit F12 on that one just to show you how many different attributes you could have. Okay, we got quite a few, and a lot of these can be bitwise or together to combine a couple of them. And then the very last parameter there would be a handle to some kind of template file, but we really don't care about that for right now, so we just say nothing, all right, just null. And then just being good, trying to do a little bit of error checking to make sure that the file was actually created successfully. We didn't have any kind of error come up, so we do a little check against a constant here of invalid handle value against what we should have is a legit handle. And if it fails, for whatever reason, we'll go ahead and just print out a little message and we'll call get last error because CreateFile, if it fails for whatever reason, it'll go ahead and set some errors, some error codes for us. That way we can go ahead and get them. And we're actually not going to be doing anything with this handle. The only thing we're going to do right now is just go ahead and close it. All right, we're done with it. We don't need it anymore. Just a showcase, if you will, about how we call CreateFile, pass the parameters to it. Okay. All right, so this is going to be compiled as a debug program for 32-bit. All right, and 32-bit for Windows APIs, what they use as a calling convention behind the scenes is something called standard call. All right, so what in the world is standard call? Okay, I'll go ahead and I'll share this link out there with everybody in Discord. All right, so there you go. That way y'all can look at too if you want on your own system. But basically, what's going on here is the documentation is telling us that for 32-bit systems, 32-bit programs, specifically like this one here, every single argument that's going to be passed will be widened to the full 32 bits. Right? It's basically the size of arguments and values that could be pushed or placed onto the stack. All right, a stack belonging to a thread. And the same thing goes for the return values. They'll be 32 bits wide as well. So for example, this number here, 0, all right, that's basically going to be extended to be 32 bits wide. So you see multiple zeros. All right, you can't just have just a single 0 there on the stack. All right, that'll be making a little bit more sense when we jump into Debugger and we start to look at things on the stack. Okay, then going further is saying that parameters are pushed onto the stack from right to left. Okay, so what does that mean? Let's break that down. If you look at how I had this in my source code, right to left really doesn't make sense. But imagine if everything was placed on a single line, like line 14. I'm not going to do that because I got all these comments and stuff in here and messes around with readability, in my opinion. But right to left, okay? If everything was on a single line, this would be the rightmost argument. Okay, right? It makes sense. All right, so we go right to left. So we start here. This gets pushed onto the stack. Then we come left one. That gets pushed, push, all the way to the leftmost, or the first argument for the program. Okay, so we'll have 7 push operations, or push instructions happening for this function call. All right, so back to MSDN. Talk about some other things that'll be saved and restored. Okay, great, awesome. And then we have some keywords about the various calling conventions like standard call. Okay, that's what we're talking about right now. And same thing, push this parameters on stack, reverse order, right to left. All right, now we can go ahead and dive a little bit deeper into the weeds with this and look at this with the debugger. All right, if you have all those files in the Discord server, Awesome. Go ahead and open up the run file, CreateFile_32.run. It should automatically be associated with WinDbg, assuming everything is installed properly and all that nonsense. But if not, you can manually open up the trace file inside of WinDbg. Okay, so go ahead and I open that up here, and we go ahead and expand that out just a little bit more. And have my timelines. Let's just shove that up here kind of out of the way a little bit. Yeah, that's fine. Just going to adjust my windows here slightly. Bring the registers. Let's put them down at the bottom half, I suppose. Okay, all right, sweet. All right, so blast from the past, right? A little TTD action yet again. Makes it nice when you don't have to worry about the binary being with you too. Okay. All right, so we can make sure we're at the beginning, G- or GTAC. Okay, yes, we are indeed at the beginning of execution for this. And looking at the modules here, we can do a little LM, and we can see that we have CreateFile as a module here, and we see the simple file for that. Awesome, cool, good stuff. Now, what I want to do though is I want to set up a breakpoint. Basically, not really on the entry point for the program, but to where the main function is about to execute. So inside of WinDbg, we have a command called BP, short for breakpoint. One thing nice about WinDbg is you don't have to specify the full word for something that you're trying to do. Like you don't have to type in breakpoint, it could just be BP. And just to show you this real quick, if you do a .hh and then a BP, or the command that you're trying to figure out, it'll open up a help window. And a lot of times, you can click on one of those, and it'll bring it up for you. Yes, click a sub-entry, whatever. Okay, so it tells you BP, BU, and BM commands set software breakpoints and give you some generalities around it, various options that you can pass to it, other flags, stuff like that. And down towards the bottom, sometimes they give you some examples of how to use some of these commands. Okay, so if you're ever like trying to explore a command or whatever, you're not sure what its full capabilities or its full potential is, go ahead and do the .hh and just open up the help page for it. Okay, so let's go ahead and set up a breakpoint. And the format for setting up breakpoints is the name of the module, a bang, and the name of the function or the symbol. Okay, so the name of the module that we are interested in is CreateFile. So I'm going to go ahead and modify that. CreateFile. And because we have symbols, it should understand the word main. And to get a listing of the breakpoints, we can just say BL. All right, so breakpoint list. There it is. We see it's breakpoint 0 or index 0, and we have a couple options. We could go ahead and disable it, which basically means even if it were to hit, it's not going to tell us it's been hit. It's not going to pause or hit or pause execution for the program. It's temporarily disabled. Clear is basically go ahead and delete and fully remove this breakpoint because we're not interested in having it anymore. Okay, so cool. We have a breakpoint set. One of the things we could do, because we're inside of a trace, we could add a breakpoint to the timeline. And so add a timeline, a breakpoint, the only one that's there, and we get a little dot. All right, cool little red dot, success. And then, sweet, right? So because I have the source over here, and y'all do have the source over there too, it's just in Discord, gotta go get it. it'll go ahead and jump us to that moment of execution when main is about to be invoked. Okay, awesome. And I'm going to minimize the source code view just a little bit. Okay, cool. Now, I don't want this to be a full-blown intro to assembly here, but we'll have to cover some assembly basics because obviously we're seeing some assembly. So I will talk about some of that stuff, but not going to do a full-blown introduction here, trying to stay on topic for calling conventions. All right, so we go through the motions here, look at some of these instructions inside the disassembly window, and what we're looking for is our call to CreateFile. All right, which we don't really see. I mean, we see something here with CreateFile, but that's the name of the module. Okay, but instead, what I'm looking for is we have this weird looking kind of value here, and we're calling that. All right, so we're gonna have to explore that because I think that's where we're going. And right before that call, we have a lot of push operations. We got 1, 2, 3, 4, 5, 6, 7. Okay, perfect. That is probably going to be the seven arguments that are getting pushed to the stack right before our CreateFile API is called. Okay, so one of the things that we can do is we can start to inspect that and check out some of these registers or check out some of the values that we're going through here to make sure it is indeed what we're interested in seeing. All right, so what we can do now is we can have execution start to happen. We're going to execute some instructions, and some of those options you have are step over, step into, or step out. And because it's a trace file, you can step out backwards, you can step into backwards, or step over backwards. So you can go left, you can go right, any which way, because it's all been recorded. So you're not really going to see much of anything new inside this trace file. Okay, so let's go forward. Just a single instruction, so F10. All right, and then when you hit F10, you can see inside of the command window the instruction or the command P. All right, so you can F10 or you can hit P in there, it doesn't matter. And right now, main is just going through doing something called a function prologue. It's setting up the stack frame that belongs to the main function. All right, so we have the instruction coming up next of move EBP, ESP. All right, ESP is just a stack pointer. Kind of tells us where the stack is pointing to at the current moment this instruction is hitting. So it kind of keeps track of where the topmost, if you will, topmost portion of the stack is right now. So that's going to be saved off. It's going to be saved inside another register called EBP, right, the base pointer. So I hit F10 to go ahead and let that happen. And as those changes are going about inside of the register's window, you can see in red changes to some of these register values. It's kind of cool. And then we'll go ahead and we're going to subtract a value from the stack pointer. And we got a value of E4H. And if you ever want to see a different format for like a number, you could do dot formats and 0x E4. Okay, the decimal value for that is 228. Okay, so this is setting up the stack frame for the main function, and it's going to be about 228 bytes in size. Okay, cool. And then we F10 a little bit more, and we see some push operations, and this aligns with what the MSDN page we're just looking at of saving some of these registers. All right, we got a little move operation there, and a move a bunch of C's into EAX, and it's rep stos. Right, rep stos. What's up with this? Rep stos, or just rep, is a repeat instruction. It's going to repeat doing whatever it needs to do a certain number of times. Think of it like a loop. Okay, how many number of times? Okay, how many times does it know to repeat? When does it know to stop? Okay, well, the repeat instruction knows to look at the ECX register, and it'll go ahead and it will repeat ECX times this right here, double pointer ES EDI. Okay, whatever's inside EDI. Okay, so it's going to store a double word from EDI, ECX times. So what is ECX? ECX holds the value of 9, so it's going to repeat that 9 times. All right, think of it as like a for loop. That's going to iterate 9 times to do a thing. Okay, so we'll go ahead and we'll F10 that. Okay, cool. That did its thing. And then we got some other instructions happening. We'll go ahead and skip through some of these. Just F10, F10, F10. Okay, now we get to our first push instruction that directly relates to our Windows API that we're about to call here. All right, now I'm going to try and draw a little bit too to help visualize what's happening just a little bit more. Okay, so let's say that we have a thread. Okay, so that blue rectangle is a thread. Okay, that belongs to this program that's executing some instructions right now. And inside of that thread, we have a couple of stack frames. Grab a different color here, and let's say, I don't know, I'm just making something up here. Obviously, none of this is to scale or anything like that. So this is the stack frame that represents the main function that is executing instructions right now. Okay, so this little red rectangle, or square almost square, is 228 bytes in size. Yeah, y'all with me on that? I hope so. Y'all are a lively little bunch right now. So we have a stack frame that belongs to main, 228 bytes in size. And what's happening, or what's about to happen, is we're about to do some pushes. So what we should be seeing is, let me go to the text here. We're just going to come down here, but right there, is we'll see it push to 0. Okay, and then right after that, we should see the push 80. And then 1, 0, 0. that looks like a crazy 8 right there. And then this crazy number here. Okay. And then whatever EAX has. I don't know exactly what EAX has right now, but whatever's inside of it is going to be slurped out and pushed onto the stack. Okay, whenever that instruction happens to execute. So that's what it's going to look like. They're pushing like right on top of each other, one after another, the rightmost first, and then going left all the way until it's done. Okay, so if I flip back over to the code, we should see something like this. Okay, that's good there. All right, so it's gonna be a lot of drawing here. That one goes there. That one there. Create new. be the 1, and then zeros. I'll skip those. And then generic right. Is that constant value there. And then look what EAX should be. EAX should be the string for the file name. Okay, so that's how you can kind of tie together the values that we're passing in from the source code side to the debugger side looking at the stack. Okay. All right, now I'll go ahead and I need to clear all that because that's getting pretty loud. Okay, I'm going to try to redraw that real quick. Just a little bit. Okay, I'm not going to do everything else. Just takes a little bit too much time. Okay, so let's see. Let's go ahead and step. We'll let that push happen. Okay, all right, the push happens. So zeros were pushed onto the stack, despite us only saying push 0. Okay, but we can't just push a single byte to the stack. It's going to be extended all the way out. So we'll see 4 bytes, okay? And what we can do here is we can do DC ESP to basically dump the stack and display some ASCII on the right side, all right? Convert some of the hex to ASCII if there's a known conversion there, something that's printable. Okay, so we see the zeros. Okay, look at all those. Right, that's it being extended out from just 1 0 to a couple of them. Okay, cool. Next, what we should see is the hex 80 being pushed onto the stack. So we'll go ahead and we're going to F10 that. Awesome. And I'm just going to dump the stack again. There we are. There's the 80. Okay. And go through again. We should see the 1 up there now. Dump in the stack. Okay, cool. All right, so you kind of get a sense for what the flow is going to be like for the rest of these push instructions. Okay, so I'm not going to bore you to death by doing that manually. We'll go ahead and step it through. And we're going to stop right here. Now remember how EAX should be the placeholder for the file name. What is it? Let's check. Let's say just dump out whatever EAX happens to hold and show us the ASCII. There it is. File.log. Yes, indeed it is the name that we specified in source that we want to be created on disk. Okay, cool. All right. Optionally, if you don't have and don't want the registers window open, it's taking up too much space or whatever, inside the command window, you can use R. Just do R, show me all the registers, or almost all the registers. And you can see what EAX holds, basically just a pointer or an address of where the string is located. And we see the null terminating character right there, the null byte, saying this is indeed the end of this string. All right, and so what's happening here at this call is WinDbg is actually smart enough to know where this is about to go. And we can see down here at the bottom of the command window that we're calling through a double word pointer for an import. Import for CreateFile A. All right, CreateFile A. CreateFile A is the ASCII version of CreateFile. There's also a Unicode version of this same function. It's just CreateFile W. Okay, you can specify either one in source. I just happen to use A just for right now. Okay, and you can see where it's going to be going, and that's going to be inside of a different module, kernel 32. And it shows us the address of that. Okay, so inside our fake little stack over here, inside of our little red square. All those pushes happened. Okay, everything's all said and done. And then something magical, if you will, or interesting is going to happen when the call instruction executes. It does a couple of things behind the scenes. One of the things that happens is it'll save a register or push a register onto the stack, right? The EBP. The EBP register is basically like the bottom pointer of the stack, if you will. And it's going to save that off because the program needs to know where to return execution once this function is done doing its thing. Say, where do I go back to? How do I return home? So that address gets saved off, and that is what is dubbed as the return address. Okay, and then the other thing that kind of happens behind the scenes with the call is the transfer of execution flow. All right, so we're no longer going to be inside of main. The flow of execution is going to change. We're going to go somewhere else. We're going to go to a different function. And that function happens to be inside of kernel 32. Okay, we're not going to do F10 because that's a step over. If we step over the call, that basically tells WinDbg that we don't care about anything that's happening inside of that particular function. Don't care. Whatever it does its thing and returns. Yay, cool. See ya. All right, but we do care, right? At least for this particular one, we care. So what we want to do instead is we want to step into the function call. I want to see what's happening inside there. I want to check out all those instructions. So if you go to step into, you can click on it, or you can just go ahead and hit F8. All right, so since I'm already over there anyway, I'll just click on step into, and there we are. Okay, but we're not quite there yet. It is actually just a jump. All right, so we did the call. The call got us right to a jump. So we can hit F10 to see where we jump to, where we land. Okay, so we went from our executable called CreateFile to kernel 32 to kernel base. And this is where the function is actually located. This is where the logic, the instructions and all that for CreateFile reside inside kernel base. I was jumping around. Okay, so let me scroll down just a little bit here. We can see it's going through the motions of setting up what's going to be setting up its own stack frame, stuff like that. Okay, and then also at some point in time, it needs to access some of the arguments that we pass to it. Okay, so how in the world could it do that? How in the world can it find some of the arguments? Well, lucky enough, it actually knows the calling convention. Okay, it knows where things should be located on the stack and in what order they should be specified. Okay, so it's basically going to look at it in the opposite way and say, all right, where's my first argument? Okay, I know where that is. Sweet, where's my second? I know where that is. So on and so forth. Okay, but it uses a very specific value or register, if you will, to do this. Okay, so let me step through. Let's F10. Okay, cool. And then push EBP. All right, push EBP just happened, and we have that now on the top of the stack. Okay, so let's say for a minute. So give me just a second here. Okay, let's say, pretend for a minute, because instruction is not actually there. Let's say that, let's choose a different color. Guess I'll go with green. That this function here also sets up its own special stack frame. Okay, so that happened, sub stack frame, And it's going to have room for local variables, stuff like that it might need to save off. Cool. And then inside of that stack frame was, let me choose a different one, it's a little bit better than green and yellow. Let's just say for a minute, that is EBP. Okay, that square is EBP. When the push EBP happened, okay, cool, great, this is where it goes. And then in order to access certain arguments or parameters outside of its stack frame, it has to do an offset, a positive offset of this value, all right, so EBP. So EBP plus 4 will always be the placeholder of where the return address should be located. Okay, so let's go through here, and I'm just going to do another small little square. And that's going to represent EBP plus 4. This one's going to represent EBP plus 8. And this will be plus 12, 16, 20, and missing out of room. Okay, so on and so forth, right? Get the idea? So you can see those positive offsets from EBP, and it wants to go to sleep on me for some reason. Okay, cool. All right, so if you look at the instructions here inside the function, we have a bunch of pushes, more pushes here. Whoops. I did not want that to happen whatsoever. I just lost all my pretty art. Yo, what's up, TPZ? Is this in relation to... No. Nope, I'm surprised you remember that terrible drawing of the linked lists. Those gave me some nightmares afterwards. All right, good stuff, man. All right, so over here, let me go ahead and highlight this. Got 1, 2, 3, 4, 5, 6, 7. Okay, we'll just go right there just to make it nice and easy. All right, and then with the different color, we have our call to CreateFile W. Right, so what you can see what's about to happen is the ASCII string that I used is now going to be converted to a Unicode string. Another indicator of that happening is this function call right here, base P 8-bit string to dynamic Unicode string. Okay, so internally, every time you're using ASCII strings for some of these APIs, Windows or the function itself is going to do a conversion from ASCII to Unicode. And then, of course, it's going to do the opposite conversion back because you wanted ASCII in the first place. All right, so cool. That's setting up everything again in a right to left order. Okay, so we go ahead and we see, excuse me, all of these arguments. Remember I told you it has to be EBP plus something to go outside of its stack frame to grab an argument outside of a stack frame. So that's what all of these are. All of these are some of those arguments that have already been pushed before, but yet they're being pushed again because we're calling a completely different function here. All right, and then also I want to draw your attention to something a little bit unique here. Let's just do yellow. That right there. And we got that guy too. Okay, so we see this little ending here, the at 28. At 28. What in the world is at 28? Okay, if you're out there in Discord, give me a guess. All right, give me your hunch or whatever you think the at 28 could be. All right, I'll give you just a moment. Gather your thought, gather your guess, fire something in there. If you're not in Discord, put it out there in Zoom chat. Oh, let me know what you think. All right, what's at 28? Memory address? No. Good guess. Good guess. TBZ, you should know this. You should definitely know this. All right. Getting closer to pointer. Getting closer yet. So let's think for a minute. How many arguments are being passed to this function? Right, how many? We said 7, right? 7 args being passed to CreateFile. And earlier I said that stack-based operations are going to be a certain size. Every single one. Every single push is going to be a certain number of bytes wide. Anybody remember that number? That magical number for all the push operations? The hex value for the amount of arguments. Yes, that is exactly right. Okay, so 4 times 7 gives us a 28. So there will be 28 bytes worth of arguments that will be coming into this particular function. And that will always be the case. There will always be 28 bytes coming in each and every single time, because for a 32-bit program and a 32-bit stack, the push operations, pop operations happen at 4-byte wide values. Okay, so very critical to understand that. It's a nice way to visually grab your attention and let you know what possible calling convention you're dealing with at that moment in time. Okay, all right, enough about that. Okay, you can go ahead and get rid of that drawing. Excuse me. All right, awesome. So I really don't care what else CreateFile is doing. Right? I don't care about the internal working operations of it or anything like that. So we can go through and we can step a few more times if you wanted to check out the stack a little bit more and see some of these pushes. And what I want to do instead is we'll just go ahead and step out of this. Okay, because we won't care about it anymore. But did it thing, cool, create a file, didn't create a file, I don't know. Whatever happened, happened. Okay, and then we're back inside of main. Okay, so inside main here, we see all the we saw that rep instruction like we did before, and we saw the call was basically calling through to a jump that gets us from kernel 32 to kernel base, and now we're back. All right, we're going to compare ESI with the stack pointer. Okay, all right, so that in a nutshell is like the down and dirty introduction for standard call and how arguments are being placed or pushed onto the stack, how the function can find those by referencing positive offsets of EBP, the base pointer. And one thing I forgot to mention inside of that, CreateFile function, let's go ahead and go back to that. Queues? Okay. All right. No, not queues. Okay. Right here at the end. RET1 Charlie or RET1C. And to get the different formats for that one, I just did dot formats, 1C, and we see decimal value of 28. Huh. How about that? So because CreateFile knows exactly how many arguments are coming into it each and every single time, it can clean up the stack. It can clean up the arguments from the stack before it returns, or in this instance, while it's returning. That way it offers a little bit of speed or efficiency, if you will, to where the function who is calling CreateFile doesn't have to do that. All right, it's kind of nice that way. It takes that burden off of the caller and says, I don't care. I don't want to deal with the cleanup. It's nasty. I don't want to put my gloves on and clean up your mess. You clean up your own mess. All right, so CreateFile does. It's like, yeah, I know how many arguments are coming in every single time. Okay, and this is important to understand too, because it doesn't matter if the values of the arguments change. They're still going to be the same number of arguments. They're still going to be the same size, all right, 4 bytes wide for every push instruction. Okay, that never changes. Okay, so this is going to be consistent for every single Windows API when we're following the standard calling convention, standard call calling convention. All right, again, this is very specific to 32-bit programs, 32-bit function calls. Okay, let me pause here for just a minute to see if anybody has any questions about standard call. Okay, it doesn't look like anything's coming in. I'll try to keep an eye on the windows just in case something pops up. Feel free, though, if you ever have questions, just type it in whenever. You don't have to wait for like a very specific moment for me to pause or catch breath or whatever. Just type in a question whenever you got one. All right, cool. So back into main, right? The function call did a thing, create a file, didn't create a file, whatever. We're back. And notice there's no cleanup happening here. There's no cleanup of any of the arguments from the stack. Again, that we are free of that burden. We don't have to do that. Okay, that's a nice beauty of standard call. So now we can go ahead and proceed on with the execution of our program and do whatever else it needs to do. Okay, I can go ahead and hit just F5 and boom, did its thing. All right, sweet. All right, that's it for that particular one. Okay. Now, what I'll do is, let me go ahead and crush this particular instance of WinDbg, and we're going to move over to, to the Cdecl. All right. So Cdecl, yet another calling convention, but Cdecl does things just a little bit different. And let's look at the MSDN documentation and take a look, see if we got Cdecl. There we go. All right, so stack cleanup, the caller. The caller is responsible for cleaning up the arguments from the stack. Okay, has a little bit of work to do. It's not too crazy. And parameter passing. Arguments or parameters are pushed onto the stack in reverse order, right to left. Okay, so nothing changes from standard call for that piece, parameter passing. The big change here will be the stack cleanup. Okay, so really, here's why. I just said that standard call functions will have the same number of arguments every single time. Well, with Cdecl, that won't always be the case. For example, printf. Printf is one of those functions that can take a varied number of arguments. Yeah, you can call it with 1 argument, 2, 3, 4, 20, any number. So printf really has no idea how many arguments are being passed to it ahead of time, so it can't do the cleanup itself internally before it returns. So the caller has to do that. That'll make more sense. We'll see that specifically in the debugger. So we still have a 32-bit program, and we have a very, very, very simple demonstration of this. Okay, just calling printf to print out a string, and the string is a formatted string. See a couple percents, right? %d, d, and something in hex. Okay, so this is argument number 1, 2, 3, 4. And those all coincide to the placeholders or the format string placeholders inside of our string. Okay, cool. Now let's go ahead and open up one of those TTD files for Cdecl. Cdecl32.run. All right, GTAC, just to make sure that we are indeed at the beginning. And I'm going to do the same thing we did for the other program. I'm going to go ahead and set up a breakpoint on main. So BP Cdecl. the bang main. And BL, just to make sure that it is stuck. All right, sweet, it's there. And just to make things easy, we'll add it to the timeline. And just jump to it. And there we are. All right, so not a lot changes. We see that the sub happening here against the stack pointer, which is our part of our prologue. It's setting up the stack frame for the main function here. And we see some pushes to save some registers that are to be restored later. And then we see the rep instruction again. And then here we see the pushes as they relate directly to our printf function call. Okay, so let's take a look at that. Let's F10 a little bit, step over some instructions, and we'll work our way down there. All right, so first things first, push D. Okay, so what in the world is that? In case you don't want to do hexadecimal math in public. Okay, there you go, 13. Let's check the source. 13, indeed. Off to a good start. And then we see the, let's step it. Okay, push 2. Step one more time. Push 1. Okay, awesome. We'll just execute that. Then we'll pause right here. Let's go ahead and take a look at the stack pointer. So I'll just do DC, ESP. And we see everything in the correct order so far. We got the 1, the 2, and hex D. Okay, awesome. And then let's go ahead and let's push that last one there, F10. Okay, but what is that? We see it's a 4-byte value. What specifically? So we can DC. Let's just go ahead and copy and paste that. There we go. That is the address of the pointer for our formatted string. This is a basic formatted string. And we see 1, 2, and hex. All right, and then instead of deciding to step over this, let's go ahead and step into this just briefly. Step into, okay, now we can go ahead and do a step over. Okay. All right, there you go. So printf is going to happen. It's going to do some things, set up its own stack frame. Okay, cool. It's going to access the arguments that have been passed into it and then do some more stuff. Okay, so cool. We don't care, again, internally what printf does. If we're really bored and you can't sleep at night, go ahead and reverse engineer and debug printf. You will be very bored. All right, so let's get out of that, huh? Step out. Okay, cool. We're done. All right, printf happens. It printed out stuff. Cool. And then we're back here. We're back here, and we see this add instruction. We're adding something to ESP. Okay. We're adding the value 10 hex. So 10 hex should be 16 in decimal. Can anybody take a guess? Anybody want to make a wager as to why that particular value? Why 16 bytes? Okay, it's going to be very similar to before when we're looking at CreateFile. It had the @28 at the end of that. Yeah, 4x4. Yeah, not talking about trucks. Yes, 4 arguments being passed to printf. Yeah, 100%. Yeah, good job there, TPZ. All right, so you can see here, because the printf did its thing and it couldn't do the cleanup before it returned, that responsibility is now pushed off to us. And so the add ESP is one such way to do a cleaning, if you will, a cleansing of the arguments from the stack. So we'll go ahead and we will adjust the stack pointer to basically jump or make an adjustment of 16 bytes on the stack to go and get back to where we need to be. Okay, so we just do a little dump of ESP. Excuse me. Okay, so here's where we are now at C94, and we're basically pointing right to the address of where the formatted string is. Okay, but we don't need these values anymore. They don't need to be on the stack. Okay, that was just for printf. We don't need them for anything else right now. So we'll go ahead and make an adjustment to the stack pointer, and in essence, we're gonna jump right over them. Okay, so let's go ahead and F10 that. Boom, we did the adding there. Let's go ahead and check out the stack again. Okay, and then look where we are now. Check that out. That's 16 bytes. Just so happened to jump us right down to here. So now the stack pointer comes right here. And even though we cleaned up the arguments from the stack, they're still there. Okay, so let me show you that. Look at that. Okay, still there. But so we didn't wipe them out, right? So it's not a true clean, if you will, or a cleanup or anything like that. We're just accounting for that space that was there on the stack for printf to do its thing. And then when it's done, we readjust. Okay, we readjust the stack and we skip over them. They're null, they're done, we don't care about it anymore, and we're moving on. Okay, but still there. Okay, one little soapbox statement here for that. This could be called garbage values. Inside of a function, when you're declaring local variables, if you choose not to initialize them for whatever reason, they will be initialized with something. Okay, it's not every day that the compiler and stuff will give you a value of 0 to initialize it for you. By default, it says, hey, silly, you're not doing that. Let me do it for you. So you could get garbage values. This stuff that's still there on the stack could be assigned to one of your uninitialized local variables, and this could be junk. This could be garbage. Okay, maybe you don't want some of that to be there. Yeah, null could be there, whatever. All right, but you don't want to have garbage values inside your local variables. You want to initialize them right away, as quickly as possible to avoid any of that stuff. Okay. All right. Then XOR happens. All right, we XOR EAX. So anytime you XOR something with itself, the result is going to be 0. Okay, so printf actually returned a value to us. It returned a value of 43. Pretty much, you can take this to the bank. When functions return a value to you or to the caller, they're done inside the EAX register. And let's see what hex 43 is in decimal. All right, dot formats 43 is 67 in decimal. Basically is telling us how many bytes printf actually printed out. Okay, so EAX is about to be zeroed out, so F10, and boom, you can see that change inside the register window, and we're good to go. It's all 0. Okay, so Cdecl, not much to it, right? Now that we talked about standard call, the transition into Cdecl is rather easy. A lot of the traditional C type of functions, like printf or any kind of variable, like var_arg kind of function, a lot of times will be a Cdecl calling convention, because it doesn't know, it can't predict with any kind of accuracy how many parameters are being passed to that function. I just chose printf because it's a perfect example of a var type of function. All right. And let me check Zoom and Discord, make sure nobody has any questions. All right, cool. All right, so now we talked about 32-bit programs, standard call and Cdecl. Okay, now we get to move over to 64-bit and take a look there. And let me go ahead and crush this one. For the 62-bit side of the house, we're going to use this exact same code base, but just going to compile this down to a 64-bit program. And you're going to see how we make a pretty big jump in difference from how 32-bit parameters are passed to a function to how 64-bit parameters are being passed to a function. All right, so now if you have those trace files, go ahead and open up the CreateFile 64.run. And make sure at the beginning. And just like we've done the previous 2 times, we're going to set up a breakpoint on main. So CreateFile, bang, and then main. We'll list it to make sure it's going to go. Cool. Add it to the timeline just because. Just click it. We'll go ahead and jump forward in time. There we go. Okay, we see the traditional function prologue happening here from main. The sub is setting up and creating the stack frame, so 150 bytes. Looks like it's decimal 336. So main in this instance is going to have a stack frame of 336 bytes in size. And then we'll go through here. We'll see a couple other repeat instructions. Awesome. And here we now get to our call. If I click on this address, the address of the call instruction, let me copy this. And inside the command window, I want to set up a breakpoint on that address. All right, so breakpoint has been set. We see that there, and we also see, hey, all right. I forgot that some things are clickable inside the disassembly window there. We can see that the instruction is highlighted red. Okay, cool. If you want to see that in a timeline, you can add that there. All right, poof. There you go. It's on timeline. Okay, now here's what happens for CreateFile. Okay, same Windows API we talked about for 32-bit, but we're just changing the architecture, moving from 32-bit to 64-bit. So here's what happens. 64-bit, we now get to heavily utilize registers. All right, it makes things a little bit faster. Accessing values and moving values to registers is very, very fast. And so what we have for Windows specifically is the first 4 arguments are going to be in registers. Okay, so argument number 1 is going to be in RCX. Okay, so let me go ahead and now we have the breakpoint there. Let's just F5. Well, actually, no, I don't want to do that. We're going to go right to that one. Okay, for those following along at home, basically what I was looking for here is the move 0 into this offset from RSP, from the stack pointer. Then I'll hit F5 and we'll stop there. Okay, so we get to deal with registers now. Registers can hold a lot of information compared to a 32-bit register. right? It's double in size. Stack-based operations are also double in size. So if you were to ever see like a push instruction or something like that, it's instead of being 4 bytes, it's going to be 8 bytes. Okay, so knowing that, the amount of bytes that are going to be passed to a function is obviously going to be a whole lot larger. All right, now to try and find these arguments that are being passed to the function, they're in some different places. So how do we find them? I was mentioning before that the first argument is shoved into RCX. So we can go ahead and try to take a look at RCX to see what it is right now. So we'll GC RCX, and it's like, no idea. All right. So let's go ahead and step through a little bit so we can check out RCX. F10, F10, F10. And as you can see, these are the same values that we're passing for CreateFile, just like the 32-bit. Okay, XOR, XOR, and then we'll shove the generic write into EDX, and then RCX is ready to rock and roll. Okay, so now we can check out RCX. We'll just DC RCX, and there we go. We see the address of file.log, right? The address of our string for the file name. Okay, so RCX has that first parameter. Cool. Where's parameter number 2? Parameter number 2 is going to be in RDX or EDX, and it's going to choose one or the other based on the value, the size of the value that needs to be shoved in there. So the hex value here, remember that's the constant, the value behind the constant of generic write is small enough to fit in EDX. So that's what it's going to do. All right, so it's the first 2. All right, then we have R8. R8 is for argument number 3, which is 0, because we see the XOR against itself. Remember, anything XORed against itself will be 0. And then we have another XOR against R9. Okay, so R8 is for number 3, R9 is for arg4, and then the rest of them are actually going to be placed onto the stack. But not just anywhere on the stack, a very specific spot. So we'll go ahead and dump the stack. All right. So what I did there, the DQ, basically just changes the output of the command for a quad word, or a Q, Q for quad word. DC is just basically show me bytes. You could do other things like DW, DD, so on and so forth. It just changes how wide the display is. All right. So in any case, we can see right at the top of the stack, we have a value there. Okay, you can see it's been highlighted in green to show you that this address has been seen somewhere else. You see some other things that are on the stack as well. Okay, but one thing I want to draw your attention to is for argument number 5. All right, arg5 is a value of 1. It is going to be on the stack, but not right at RSP. It's going to be an offset of RSP. RSP plus 20H. All right, so hex 20 should be 32 in decimal. And if I hover over that, indeed it is. All right, 32 bytes. All right, so that little space right there. And there's a reason why. Right? The reason why is because that little space, that 32 little byte buffer, if you will, is reserved for the function that is being called. It's a little scratch pad space, if you will, that it could use for whatever it wants to use it for. Maybe it saves some arguments in there. It could, all right? And that number doesn't come just out of thin air, really. So hex 20, 32 bytes in decimal, also directly corresponds to the first 4 parameters of the function, right? So we're dealing with 4 arguments, the first 4, and remember I said instead of 4 bytes wide, now we're dealing with 8 bytes wide, okay? 4 times 8, 32. So that's how that number is coming up, okay? So you could, if you wanted to, do an offset from here inside of this to a plus 32. But you really don't need to. You want to skip it a little bit because the output here, we got E0, F0, and then the 00 here. These are the addresses changing 16 at a time. Okay, so coming in here, we can see the values that are being passed into this. So we can go ahead and try to pluck those out just a little bit at a time. See the value of 1, 80, and 0. Okay, you can see those arguments being there on the stack already, right, at RSP plus 20. And then they go ahead and they increase 8 bytes at a time. Okay, so the 1 will be RSP plus 20. Hex 80, add 8 bytes to that, be plus 28. And then the 0, add another 8, and we see RSP plus hex 30. Okay. All right. And then the call instruction happens. Remember, it does a few things behind the scenes, changing flow of execution over to CreateFile. And we can go ahead and step into that. All right, so F8. And just like the previous 32-bit version, we're now jumping around a little bit. So we're inside of kernel 32. There's no code here that implements the function, so we're going to jump. All right, so F10, we'll jump. And then that takes us out of that. And now we start going through the motions of, actually implementing the function. All right, and then, if I can see it, bit string, I'm going to do indirect call, CreateFile internal. Okay, so that's probably where the real magic is going to happen inside of this CreateFile internal. Okay, so looking at that real quick. It's all function prolog stuff. Setting up the stack frame right there. Security cookie. All right, prevent some buffer overflows. Some things are talked about in 660. So if you like all of the stack-based kind of operations, you want to dive deeper into like the whole EBP plus 4 for the return address, how to overwrite the return address, stuff like that. Highly recommend taking 660, written by my friend Steve Sims. Crazy smart guy. Also wrote 760. So a little plug for 660, 760. If you like that type of stuff, you want to exploit some of those values that are inherently dangerous on the stack, take a look at that. It could be right up your alley. All right. So going through, doing this thing, and CreateFile internal is actually like a pretty large function, pretty huge code base here, all just to go ahead and create our file, and that's it. Here we go. We're initializing a Unicode string. So again, taking our ASCII version, converting it over to Unicode, and then going to convert it back because that's what we called it with. We call it the ASCII version. Setting last errors. Converting path names. And a bunch of other stuff. Blah, blah, blah. Okay. So we can go ahead and step out. All right. So CreateFile went and did its thing. Awesome. And remember I said that EAX is a register that is used to hold the return value of a function. Well, same thing goes for 64-bit functions and calling conventions. Now, instead of EAX, now it's RAX. Okay, so RAX is going to hold our return value. And we can look at racks right now. We can see that some of the registers have changed, but racks has a value of hexadecimal F8. All right, so what's up with that? What is F8? Well, if you remember, CreateFile returns a handle, right? A handle data type. And a handle, the value F8 there is a multiple of 4. And basically what that is, it's an index inside of our process. There's a special table. It's called a handle table. And inside of this handle table are a bunch of entries that we call handle table entries, and they all coincide to a specific object that is saved inside the kernel. Okay, so that handle there at index entry F8 is directly tied to our file object that resides in the kernel. And that's how some protections or some boundaries are implemented for the objects that are out there in system space. All right, so we're taking a look at racks. Okay, we see it's a value of F8. That is indeed a valid handle or value. So when you do a little comparison against that, so again, we'll let that move instruction happen. Okay, boom. Racks happened and moved into RBP plus 38, which because we have symbols and stuff like that, the symbol file, baked into this, we know that is the actual handle to the log file, and it tells us that by giving us the name of the variable, all right, hlog file. And now we're doing a little safety check, error check to see if indeed it is a legit handle value. So that's what this compare instruction is doing. We'll go ahead and compare the hlog file, compare that handle to a bunch of Fs. All right, all of this is basically just a -1. All right, that's all it is, a bunch of Fs. And that is the invalid handle value that we're checking against for whatever CreateFile gave us. So we'll go through and do its thing, do a little check, F10, and maybe we jump, maybe we don't, right? Depending on what the result of that compare was. Okay, it's cool. We're good to go. Success happens. All right, we're set, and we'll move something into RCX. And if you look inside the registers window, what happens to be in RCX? F8. What's F8? The index in our handle type of entry that coincides or directly ties to the file object in the kernel. And we're passing that to close handle, and to say, hey, you know what? We're done with this particular file object. Go ahead and free up that resource. Get that thing out of my handle table. I don't need it there anymore. Bye-bye. So, boom, the handle is now freed. We're good to go, and the rest of the program can execute and be done. Okay, sweet. All right. Checking Zoom and Discord, see if anybody's got any questions about 64-bit. Nope, looks like everything is good to go. Okay, awesome. Get rid of that one. Okay, all right, so calling conventions, there's really not a lot to it. I know a lot of times they can seem a little bit daunting or intimidating, if you will, coming in and looking at stuff at the disassembly level, trying to make sense of stuff. But if you take some of the knowledge or some of the information that MSDN documentation gives you for the calling conventions, it basically is a nice starting point to how some of this stuff works and how you can start to navigate your way through this inside of a debugger. Okay, so we covered just a few calling conventions, standard call and Cdecl, which are specific for 32-bit. And then for the CreateFile version, we also made a 64-bit version of that and saw the specific calling convention for 64-bit function calls, 64-bit programs, and the stack-based operations, and how everything changes from 4 bytes to 8 bytes. okay, doubling in size, everything that's happening with the stack and basically with the registers. Okay, no questions over here. All right, cool. I have some parting questions for you. All right, don't feel that you have to answer right now. Maybe just drop it in Discord as you come up with the answer. Okay, so now that you know about calling conventions, let's think back to 32-bit standard call. No. What about it? What? Such a vague question. Let's think back to 670. Yeah, it's been a while. For you anyway. All right, so thinking back to 32-bit standard call, all right, how everything is placed from right to left, looking at the pushes. And if you're looking at those pushes, and right to left, tell me where you would find the value for the third parameter. Where would that be? Okay, so again, don't feel like you have to answer right now. I'm not trying to put anybody on the spot. Just some things to think about to kind of help things solidify a little bit. All right, so that's for 32-bit. Tell me where you would find the value for the third parameter. All right, switching gears, something else to think about as well. For 64-bit functions like CreateFile, where would you find the fifth parameter? Remember, the first four are in very specific places, and then anything beyond that is also somewhere else. Okay, so where in the world would you find the value for the fifth parameter for 64-bit calling convention? Okay. On the stack, is that your final answer? Yeah, cool. All right, well, officially, that's basically all I have for you today for part 3, diving into calling conventions. There are plenty of other calling conventions that are out there. These are the most commonly seen calling conventions that you're probably going to come across over your career, especially inside a debugger. For 32-bit, Cdecl, standard call, and 64-bit, of course, is probably going to be the most common that you're going to see. Some of the others out there would be thiscall, specific for C++, dealing with classes and stuff like that. One thing kind of interesting there is a unique use of a pointer called the this pointer, typically found in ECX. All right, cool. Well, if y'all don't have any questions for me, feel free to ping me on Discord. My handle is Shadows. If you have any questions or answers to some of the things I'm just asking you at the end, feel free to drop it in the CNS Workshop channel. Ping me like TPZ does all the time. Just do @Shadows with your answer, and be more than happy to confirm your guess or whatever for some of my questions. And also, if you're ever interested in taking my class, 670, I do have some upcoming runs of the course in July, DC, and then I'll be flying over to Amsterdam the week right after that. And there are some virtual options as well, because I know flying can be expensive depending on where you got to go. All right, well, since nobody has any questions, thank you all so much for jumping into part 3. I really appreciate it. I have about 3 more, maybe 2 more parts of this series. Like I was mentioned at the very beginning, diving into a few more areas, respect to various parts of the program. And then we'll go ahead and start a brand new series, Intro to C++, which I'm greatly looking forward to, as I know some of you are as well. All right, everybody, have a good one. See you next time.